Yeah, hello. My name is Domenique Freund. I'm here from LASP, from CO Boulder, and I'm zooming way more out now, so I'm looking more at space physics and specifically at Aurora at Jupiter. And so we're interested in the diffuse Aurora region there, and I first wanted to talk a little bit about how is Aurora even produced at Jupiter, and what is the diffuse Aurora region, and why do we care about it. So the Jupiter Jupiter in the first place is like a way bigger system than Earth. So if the sun erupts, basically Jupiter gets hit, but there's this magnetosphere which protects Jupiter from all the particles that would hit the surface. Particles can then enter the pole and produce those, what we also have on Earth, those northern lights. But then we also have particles that are already trapped inside of Jupiter. And this is a big difference to what we actually see on Earth. So in Jupiter, we're having those different moons that are in the magnetosphere. So we have Io, we have Europa and Ganymede. And those are, especially Io, kind of spice out a lot of particles. So there's 1 ton of particles coming out of the moon per second, and it kind of feeds this whole magnetosphere. And so there are a lot of particles are in this magnetosphere, and they can then enter the atmosphere and potentially being lost in the atmosphere and also heating up the atmosphere. And we're trying to understand how many particles are actually going into this region, to understand heating in this region, and potentially being able to also compare that to Earth and also imply what also similar processes going on, or understand processes at Earth better. And so what we exactly see is when those moons emit those particles, we're seeing those footprints in the auroral lights. So here we see a picture from the auroral lights from the Hubble Space Telescope, and we can see actually those footprints from Io, from Ganymede, from Europa, where those particles enter the atmosphere, and we see this basically light emitted. We are interested in this diffuse aurora region. So this is the main aurora region, but we are more interested in the diffuse aurora and how much input is coming actually in this region. And so if we're zooming in, we can see it here even better, where the diffuse aurora is a little bit outside of this main auroral oval. And so we're asking the question if this region is actually significant in energy input. So how are particles now actually being trapped in the magnetosphere, and how do they actually move in the magnetosphere? So we have Jupiter with its rotational axis, and you have the magnetic axis where the magnetic field is also then producing the magnetosphere a little bit offsetted to the side. The planet is of course rotating, and so do the particles that are trapped within the magnetosphere. So they are basically drifting around the planet, while at the same time also bouncing back and forth. So they undergo all those motions at the same time, and they also undergo a gyro motion. So those movements are all at the same time. And so this is also actually how they're getting trapped in this magnetosphere. They undergo those motions, and they just are trapped and following the passes. But then it can also happen that they're lost in the atmosphere producing the aurora. So how does that happen? That has actually happened with something we call the bounce loss cone. So when you actually imagine the stone here, when you skip a stone over a pond, you expect the stone being the particle and the water being the magnetic field strength of the in the atmosphere. And you're skipping the stone, you're skipping it with a pitch angle over. So while the particles drifting around and they're bouncing just like a stone over a pond with a specific pitch angle. This pitch angle then might be high enough and the tension is high, but if there's a disturbance and the magnetic field is weaker, we might need a bigger pitch angle to actually skip it. And so this is what we then call the bounce loss cone, and we can calculate that for different longitudes depending on the magnetic field strength. And for different longitudes, we need higher angles to actually keep the particles skipping or the particles falling in. And so this is what we have to calculate first, and what we can then apply to actually our Juno data. So this is the spacecraft we're using to get the data. We're using this instrument with the 90 and 270 degree sensor, and this is then the data we are looking at. So this is differential initial electron flux, so basically the flux that the spacecraft is measuring in its pitch angle over the precession of the orbit. What we just calculated, how high the angle is of the stone skipping or the particles, this is basically this line. And so we can say everything below this line, where basically the angle was not high enough to skip further the stone, this will be actually lost in the atmosphere. And so we can then actually see how much particles will be lost, and we see, for example, in those plots, especially that a lot how this is like changing in longitude. So we can actually see that most particles will be lost in the higher and lower longitudes, and less particles will be lost in this region, which is potentially actually due to exactly the shape of the bounce loss cone shape. So while the bounce loss cone is higher, we're having more particles going in, and then it goes slower, and basically while the particles drifting in this direction, a lot of particles will be lost here, and first it has to refill, and so there will not be particles to really enter the loss cone in between. So yeah, from there we can like get the total energy input, and actually we see that it's very significant overall if we're comparing it to the total energy input also from the main Aurora. So that's very significant, and that's where I always see there the stress. So yeah, thank you very much.